Welcome to Multivariate Calculus. Today, we are going to explore functions of several variables, a powerful mathematical tool that helps us model the complex, multi-layered world we actually live in. Whether you are looking at weather patterns, economic models, or engineering designs, outcomes rarely depend on just one factor. By the end of this lesson, you will understand how to handle multiple inputs simultaneously. Let us start with a simple analogy to build our intuition. Imagine you are baking a cake in your kitchen. The final taste and texture do not depend on just one single thing, but on the amount of sugar, the temperature of the oven, and the time spent baking, all working together. In mathematics, standard functions take just one input, like a simple vending machine. But real life is rarely that simple. To describe complex situations like the weather, we need functions that can handle multiple inputs at the exact same time. Now that we understand why we need multiple inputs, let us look at the formal mathematical rules. A function of several variables assigns exactly one output value to a specific group of input values. The domain is the set of all valid inputs you can safely plug in without breaking mathematical rules, like dividing by zero or taking the square root of a negative number. The range is the set of all possible outputs. Think of it like a GPS. You input a latitude and longitude pair, and it spits out a single number for your elevation. This brings us to the mathematical notation that represents these concepts. We write z equals f of x comma y. Here, the letter f represents the function or the mathematical rule we are applying. The variables x and y inside the parentheses are the independent variables, meaning they are the inputs you freely get to choose. The variable z is the dependent variable because its final value depends entirely on what you chose for x and y. If either input increases or decreases, the output z will change accordingly based on the specific rule defined by f. Before we move on, let us see this with a concrete example. We want to find the value of the function 2x plus 3y squared, specifically when x equals 4 and y equals 5. We are given a specific pair of inputs, and our goal is to determine the single numerical output that this rule produces. To solve this, we carefully substitute the number 4 for every x and the number 5 for every y in our formula. This sets up our equation for the final calculation. Continuing with our calculation, we must follow the correct order of operations. We square the 5 first to get 25 and multiply 2 by 4 to get 8. Next, multiplying 3 by 25 gives us 75. Finally, we add 8 and 75 together. The final answer is 83. If this function represented the cost of buying 4 apples and 5 boxes of strawberries, the total cost would be exactly $83. We have successfully evaluated our first function. Now that we have evaluated a simple function, let us look at one where the domain is restricted. Consider the function f of x comma y equals the square root of 16 minus x squared minus y squared. This formula comes from the geometric equation of a sphere. In mathematics, we cannot take the square root of a negative number if we want a real number as an output. Therefore, the expression inside the square root must be greater than or equal to 0. If x or y become too large, the expression becomes negative and the math breaks. To find the domain, we set up an inequality based on our rule. We write 16 minus x squared minus y squared is greater than or equal to 0. If this expression were negative, the function would break and fail to produce a real number. Setting up this inequality is always the first step when finding the domain of a square root function. Next, we want to rearrange this inequality to make it easier to understand visually, so we move the variables to the other side. Continuing our rearrangement, we get 16 is greater than or equal to x squared plus y squared. Flipping it around makes it easier to read from left to right. X squared plus y squared is less than or equal to 16. In geometry, x squared plus y squared equals 16 represents a circle centered at the origin with a radius of 4. Because of the less than or equal to sign, our domain includes all points exactly on that circle and all points inside it. This is our final valid input region. Let us visualize what we just calculated. In this diagram, the flat shaded circle on the bottom floor, which is the xy plane, is our domain. It represents all the valid pairs of x and y you can safely choose without breaking the math. For every point in that flat circle, you move straight up to hit the dome surface. That vertical height is your final output z. If you pick a point outside the flat circle, the function fails. Now that we can visualize these functions, why are they so important? Functions of several variables are the absolute foundation of modern science and engineering. In the real world, nothing happens in a vacuum where only one variable changes at a time. An economist uses them to predict inflation based on interest rates and employment changing simultaneously. A mechanical engineer uses them to calculate stress on an airplane wing depending on wind speed and air density. Without them, we could not design safe buildings or predict the weather. To summarize our topic today, functions of several variables allow us to model outcomes that depend on multiple factors at once. We learned that the domain is the set of all valid inputs that keep the math working, and evaluating the function gives us a single output. By understanding these rules, you have taken the first step toward modeling complex systems in mathematics, physics, and engineering. Great job, and keep practicing.